Two symbols show up again and again across physics and engineering: the upside-down triangle with a dot and the upside-down triangle squared. They run through the fluid equations, the heat equation, electricity, and magnetism. They look like secret code. They're not. Each one is a single, concrete, physical idea, and once you see what they measure, you'll read them on sight. Let's take them apart, starting from the symbol they're both built on. That upside-down triangle is called nabla or del. On its own, it isn't a number. It's a vector whose entries are not values but operations. Take the derivative in x, in y, and in z. A vector of slopes waiting for a function to act on. That one idea is the whole trick. Everything that follows is nabla, combined with a function using the ordinary operations you already know from vectors. Apply nabla straight to a scalar function, say, the height of a hill at each point, and you get the gradient. Each entry is the slope in one direction, so the result is a vector. It points in the direction of steepest increase, straight uphill, and its length is how steep. Hold on to the gradient. We need it to build the second symbol, but first, the divergence. For the divergence, take nabla and dot it with a vector field, a field that has an arrow at every point, like the velocity of a flowing fluid. A dot product multiplies matching components and adds. So nabla.f is the derivative of the x component in x, plus the y component in y, plus the z component in z. The result is a single number at each point. What does that number mean? Picture a tiny box around the point and watch the field's arrows. If more flows out than in, the divergence is positive. The point acts like a source, a faucet. If more flows in than out, it's negative, a drain. If what flows in also flows out, the divergence is zero. That's exactly the quantity we kept computing in the derivation videos, the net outflow per unit volume. When you saw nabla.ρu, it was literally the rate mass leaves a little box. Divergence measures spreading. Now the second symbol. Take a scalar function, find its gradient, a vector of slopes, and then take the divergence of that. Divergence of the gradient, written out, is the sum of the second derivatives in x, in y, and in z. Because it's nabla dotted with nabla, we write it as nabla squared, the Laplacian. Here's the picture that makes it click. The Laplacian at a point compares the value there to the average of its immediate neighbors. If your neighbors are higher than you on average, the Laplacian is positive, you're sitting in a dip. If they're lower, it's negative, you're on a bump. That's why it governs smoothing. Heat flows so that temperature loses its bumps. In the fluid equations, mu nabla squared u is friction dragging each parcel toward the average velocity of its neighbors. The Laplacian measures how much you stick out, and diffusion works to erase it. And that's why the notation is so good. Treat nabla as a vector, and every operator becomes familiar. Algebra. Nabla on a scalar is the gradient. Nabla dotted with a field is the divergence. Nabla crossed with a field is a third cousin called the curl, and nabla dotted with itself is the Laplacian. One symbol, the whole toolkit of vector calculus. So, 3 things to remember. Nabla is the vector of derivatives. Nabla dot tells you how much a field spreads out from a point, source, or sink. And nabla squared tells you how much a value differs from its neighbors, bump or dip. Read them that way, and the equations stop being code and start being sentences. That's all for this video. Tell me what you want to see next in the comments.